The screen is visible.
No, sir.
Now you will see whether it is visible or not. Now it's okay, visible?
Yes, sir.
Okay.
Yes, sir.
So we will start with the implementation of overcurrent relay using induction disk. So implementation of the overcurrent relay using the induction disk. Now let us consider in order to understand the working of this type of relay, that is the induction disk type relay, we have let us see that how the torque is produced by the two alternating fluxes acting on the same metallic but the non-magnetic rotor. So we have this rotor, which is metallic non-magnetic rotor. Now in this case, we will have the flux phi1 and the flux phi2. So we have the flux phi1. Let the flux phi1 is given by phi m1 sin omega t. Then we have the flux phi2. It is given by phi m2 sine of omega t plus theta. Now let us suppose these two fluxes acting on this metallic non-magnetic disk. Now you will see, because of that flux, the eddy currents are generated when the flux cuts that this non-metallic non-magnetic disk. Then the voltage is induced and the current is produced, as you know about that. So these eddy currents are there. That is, we have the eddy current due to the phi2 is equals to which is I phi2, and because of the phi1 we have the I phi1, and the direction of the eddy current is the different from the direction that we experience by using the corkscrew rule. So we will have this. In that very case, we have, if the flux direction is this, then the current direction is this. Since this is the induced current due to the flux phi1 and phi2, so the direction is opposite to that, what is in this case. Now, this is the current. Because of this flux phi1, we have the induced current I phi1, and because of the flux phi2, we have the induced current I phi2. Now, you will see that these two, this flux phi1, in this case, we have, it will interact with the current phi2 at this point. This is the flux phi1. It will interact with the current phi2 at this point, and this phi2, flux phi2, it will interact with the current phi1 due to this disk. So we have the current phi1, it will interact here. Now, from the Fleming's left-hand rule, you can find out that the force is acting in this direction for the interaction of the flux phi1 and current I phi2, and the interaction of flux phi2 and this I phi1, we are getting the force F2. So we have the force acting F1 due to the interaction of phi1 and I phi2, and due to the interaction of phi2 and I phi 1, we are getting the force F6. So the force is produced in that very case. Now, let us suppose that we have the flux phi 1 and the flux phi 2. Now, the flux phi 1 is given by phi m1 sine of omega t, and phi 2 is given by phi m2 sine of omega t plus theta. Now each flux will induce a voltage in the disk and the give rise to induced current. That is the I phi 1 and I phi 2 that we have seen here. And let us assume that the eddy current path has the negligible inductance. So in that very case, the current I phi 1 is given by I phi 1 is equals to, is proportional to, that is L d phi 1 by dt. So that inductance is negligible in the eddy current path. So it is proportional to d phi 1 divided by d t. Phi 1 we have, and we differentiate it. We get omega phi m1 cos of omega t. Similarly, we will have the current I phi 2. So this current I phi 2 is given by, is proportional to d phi 2 by dt, which is equals to omega phi m2 cos of omega t plus theta. Now from this figure, you will see that the interaction of phi 1 with I phi 2, it produced the force F1 from here. And the interaction of phi 2 with I phi 1, it produced the force F2, which can be obtained by the Fleming's left-hand rule. So let us assume that omega to be constant, then F1 is given by phi 1 I phi 2. That is interaction of phi 1 with I phi 2, which is proportional to, substituting the values, we have phi m1, phi m2 sine of omega t cos of omega t plus theta. Then again, we will have F2 equals to interaction of phi 2 with I phi 1. It is proportional to phi m1, phi m2 sine of omega t plus theta cos of omega t. And net force between the two is equals to the difference between the two. So the net force is F2 minus F1, which is proportional to phi m1 and phi m2, and finally sine of omega t plus theta cos of omega t minus cos of omega t plus theta sine of omega t. And when we solve it by using the different identities, the geometric identities, we are getting F2 minus F1 is proportional to phi M1 phi M2 sine of theta. So this is the final expression. Now, from this expression, certain conclusions can be drawn. Now, the first conclusion from this expression is that, let us suppose that some conclusions can be drawn from this. Now, first conclusion is that when we have the two alternating fluxes with the phase shift, so two alternating fluxes with the phase shift is needed for the torque production. So we have the force, the torque is also there. So two alternating fluxes are required to produce the torque. However, phase shifting should be there. The single alternating flux cannot do that purpose. So two alternating fluxes are required for the torque production. And the maximum torque is produced. In this case, you will see that this is 90 degree. Then we can say that the force is maximum, torque is maximum. So the maximum torque is produced when the fluxes are shifted by 90 degree. That is for T maximum, theta should be 90 degree. Third conclusion that can be drawn out of that is that the resultant, you will see that this time factor is not coming into picture. We have the theta only. So it is not a function of time. It means that the resultant torque is steady. Resultant torque is steady and not as function of time. And it's not a function of time. It's resultant torque. It is not a function of time. That is, D is not involved in the expression. So in this case, you will see in an overcurrent relay, as we have read in the previous lecture, that in the overcurrent relay, we have only one input. That in the overcurrent relay, as you have seen in the last lecture, that in the overcurrent relay, we only have this one input current. And here we have the time setting multiplier, and then we have the plug setting, and we have the trip contact, which is normally open. Now, we have only the one current input is there. So as per this conclusion, whatever we draw from what we have drawn from this discussion, that two fluxes are required, which are not in phase to produce the torque. So for that, and since the input of that is only the current, so how we can do that? So we are using the shading ring for that very purpose. We are using the shading ring for that very purpose. What the shading ring will do, it will lag the flux by some angle. Though the flux is moving in the same direction, let us suppose that we have the two sections of that. And here we have the shading ring we have used. Then we have this flux and this flux. So phi 1 and phi 2. So it is produced by the same current. However, in the flux, we can create the phase difference by using the shading ring, that this one lags this phi1. Now, the construction, let us discuss here. Let us have a diagram and then we can discuss that different things that are involved in this type of structure. Now, this is a diagram of that induction disk type relay. Now, in this case, you will see, as we have discussed the plug setting previously, in the last lecture, we have discussed the plug setting that we inserted the plug for getting the different number of turns and getting the different value of the current. So plug setting is in the case of electromechanical relays. Now, this is the shading coil which is used for creating the phase difference between the two fluxes to produce the torque. This is the disc. This is the control spring that is used for controlling torque. This is the permanent magnet which is used as in damping for prevent the damping. This is the time setting multiplier. That what we mean. What it means that we will rotate that. We rotate that whatever the time is required, we can set by using that rotation. So this is the time setting multiplier, and this is the plug setting in this case. Now, from this you will see that two fluxes shifted in the time phase are obtained by using the shading coil, that is phi1 and phi2. So two fluxes are obtained. Whatever torque, our main purpose is the production of the torque, so we obtain that by this shading coil. And the torque in the shading coil, that is the flux in the shading coil lags. It lags the main flux. Since the torque in this case is produced, that is, if you have force is proportional to phi m1 and phi m2. It means and phi m1 and phi m2 is due to the current only. So torque produced in this case is, that is the deflecting torque. We can call it as a deflecting torque. Deflecting torque. So it is directly proportional to square of current because two fluxes involved in that. So we can call it as a deflecting torque. It is directly proportional to the square of the current. Now, the deflecting now this spring, as we have seen, that this spring, it will actually provide the controlling torque. That is, controlling torque is provided by the spring. So, and this controlling torque is actually it is considered to be the proportional to the angle delta. Now, what is this angle delta? Now, the angle delta, let us suppose that we have two positions, this position and this position, from which we have retarded the backstop to this position. So this position is known as delta initial position, and this is the position at which, let us suppose that delta is equals to 0. So this portion, it represents the angle delta. So what the delta means? So it means that that is the angle through which backstop has been retarded for the time adjustment dial. What we do, we will retard that in such a direction so that that time can be adjusted in this electromechanical system. So this is known as this is the angle delta. That is what we do. We retard the angle delta so that we set the time that it will operate at that particular amount of time. Now, this permanent magnet, it provides the damping. That is, when it reaches the position, whatever is the main position, then it has to damp the oscillations, and which is this damping torque. This torque is known as the damping torque, and the damping torque is coming into picture only when the disc is in motion and is proportional to the rate of change of delta. So d delta by dt. Now we will have the three kind of torques. One is the deflecting torque, then controlling torque, and then is damping torque. Now, this torque equation can be written as, we can write this torque equation as deflecting torque, then we have the controlling torque, and then we have the damping torque. So deflecting torque, it should be greater than controlling and the damping torque when it operates. Now, write it in terms of, we have to convert it into equivalent. We have to use the proportionality factor also. So deflecting torque is proportional to I square. So we can use K I square, which is greater than controlling torque. So controlling torque is proportional to delta. So we can use the, let us suppose that we use some constant S in that. So S delta. And for the damping torque, let us suppose that we are using the D as a constant, and it is proportional to d delta by dt. Now, in this case, you will see that K is the deflection constant. K is the deflection constant, and this S is the spring constant. And you can say that D is the damping constant. And this actually depends upon the design of the relay. These constants are actually the function of the design of the relay. So depending upon the design of the relay, these constants can be changed. Now, when the relay is on the verge of deflection, in that very case, all the three torques are equated. It means when the disk is on the verge of deflection, that is, on the verge of deflection, we will have d delta by dt plus k1 delta plus minus k2 I square equals to 0. No, we have one more set of coefficients, that is k1 and k2, and the k1 in this case is given by S by D, and k2 is given by k by d from this. Now, this is the first order differential equation, and as we know, the solution of the first order differential equation, it is given by delta is equals to k3 e minus t minus k4. Now, we have one more set of coefficients, that is in this case we will have k3 and k4. These are actually the function of this one, k1 and k2, and which are itself the function of S, D, and K. So some conclusions can be drawn from this equation. So this is the final equation of this delta. Now, at t equals to 0, as I told you that at t equals to 0, the value of delta is delta initial. That is, we have retarded that backstop to the position at time equals to 0. And when t equals to t operational, that is when it wants to operate, then at that very time, the delta is equals to 0 that we have discussed. Now, we can find the operating time, that is t operating. We can find the operating time by finding the value of t for which delta becomes 0. So we can, in this case, in this way, we can find the t operating. Now, this initial, delta initial that we have already discussed, it can be obtained by the time multiplier setting. So we have the time multiplier setting here. We have the TMS. So we have this delta initial that we can, what we do, we can retard it, the backstop to this, we can rotate this and move the backstop in so that the time is whatever time we want to fix, we can fix that particular amount of time. So this delta initial is decided by the whatever our application is and how we can use that for our purpose. That what type of relay it is used for, and what's the main application of it is. So this is the main construction of induction disk type relay. Now come to the application. So main idea of this type of relay. So to give an overview of that, what is the relay? What is relay all about, and how it works? What's the basic principle of that? Because that basic principle is used in all other relays. So that's the main idea. Now, we have to discuss a small problem statement, and then we can find out the answer of that. Now, we have to, this is a small diagram of feeder. So we have to do the feeder protection. So application of heading would be application of that we have discussed in the last lecture, definite time overcurrent relay, DTOC. Definite time overcurrent relay for the protection of distribution feed. So application of definite time overcurrent relay for the protection of distribution feeder. So how you know the distribution feeder? We have a source and we have the load at, you have different buses. So this is the distribution feeder. So this is the representation of single phase representation of three-phase feeder. So what happens if our system is balanced? In that very case, what we do in a balanced system, as you already know, that they are, the difference between these is 120 degree. So what we do, we can represent it by a single line diagram and find out the result for all the for this one phase, and for the other phase we can get the result by rotating it by 120 degree. So that's why we have the three-phase system, so we can represent it by a single phase or single line diagram. So that's the main idea behind that. So it's a three-phase feeder, and we have, in this case, we have the three line sections. A, B, we have this two line sections, sorry, bus, this one, A and B and C, two line sections. And let us suppose that DTOC relays are used for that very purpose, definite time overcurrent relays. That is, it is used at this bus A, and it is used at the bus B. And we have the loads, this ILA, ILB, and ILC at all the buses. So the protection, we can have the protection statement, that protection problem or the protection statement. Now the protection problem is stated as, given the magnitude of, given the magnitudes of all the loads and fault currents at the buses, and the fault current at the buses, how to set the DTOC, definite time overcurrent relays at buses A and B, so that entire feeder gets overcurrent protection entire feeder gets the overcurrent protection arranged as primary and the backup protection. So this is the protection problem that we have to solve. So we are given the magnitude of the loads, that is LA, load LA, LB, and LC, and the fault currents. So we have to set these two relays, this one and this one, at the buses A and B, so that the entire feeder gets the overcurrent protection arranged in primary and the backup protection. So this is the problem statement. One more point is that, as we have seen, that as the fault is moving towards the source, the fault current increases. So here the fault current is more as compared to this point. This is due to the fact that the current is given by this source E divided by ZS source impedance, and ZL, that is the impedance of line. So at this particular point, if you see at this particular point is this impedance of the line is appreciable. So when the impedance of the line is appreciable, then in that very case, the current is less at this point. Now, as we are moving towards this area, as we are moving towards the source, the impedance of the line is getting reduced. And as a result, the current is increased. And at this point, if you see at this point, this impedance of the line is 0 because we don't have the line at this point. So we are having only ZS. It means that ZS effective impedance is reduced, and as a result, we are getting the increased value of the current. So one point is there that as we are moving towards the source, the fault current is also increased. So as we move towards source, fault current increases. So this is the problem statement. Then this statement you have to solve. So today we can stop the lecture here only.